Hello, ladies and gentlemen. Today we're going to talk about E. E, that's right. Not pi, not I, but E. So what is this E that I speak of? For today, you're going to need your notes, something to write with. Calculator is especially handy. If you have a graphing one, that'd be great. And we're going to make a couple graphs here at the end. So let's think back. Don't write this part down. We need to remember pi. Remember pi from geometry? And we used pi. What does it represent? So remember that pi represents 3.14159, you know? It represents an actual decimal value. Okay, this is irrational. It continues on and on and on and on forever here. But those are a few of the first digits there of pi. So what if you had an expression that contains pi? Could you still simplify with it? Well, sure. This is 5 pi squared. That means you're taking it times itself. So you'd have 5 pi times another 5 pi. That'd be 25 pi squareds. It's the same thing as those rules of exponents we talked about, giving the squared to the 5 and putting it on the pi as well. And now if we wanted to, could we actually find a value for this expression? Sure, we could type that in our calculator and get a numerical answer. We could do the same thing with this one right here, 15 over 20. We would simplify that, and then we would always move those negative powers up here, and we'd end up with pi to the 6th up on top, and 15 over 20 is 3/4. Okay, so we can simplify with pi, and we could take it a step further and actually figure out what this is by typing it into a calculator to get a decimal value. So pi is just a letter, or a Greek letter in this case, that represents a number. So the same thing's going to happen with E. E is called Euler's number. Okay, Euler's number. E is approximately 2.71828, but for our case, we're going to think about it as 2.71. Now, it is one of the most important numbers in math, along with understanding I and pi. It's something that you see quite often. So could we simplify expressions that contain this E? Of course you could. Just like you do x's or pi's or whatever, you can still use your rules of exponents to help figure this out. So write these two in your notes. We have 2e to the negative 3 times 6e to the 5. And we would take these big coefficients here. 2 times 6 is 12. And then what power would we have on e? We'd take these two and we'd add them together. Negative 3 plus 5 is 2. So we'd have 12e squared. Could we take it one step further and actually figure out what this is in a calculator? We could. In just a minute we will. Okay, let's take a look at this other one over here. 24e to the 8th divided by 4e to the 5th. Now if we just did the 24 over the 4 here, that would be 6 over 1 essentially. E to the 8th over e to the 5th. That means we have 8 little e's being multiplied on top, 5 little e's being multiplied on the bottom. If I simplified, I'd have e to the 3rd up on top. Remember, we subtract those exponents. So like I said, these are our simplified versions, but let's say we actually have to evaluate or find an actual value for them. So now if we were to evaluate each one, let me try that circle again. Here we go. Evaluate each one. Could we actually get a value for it? And the answer is yes. Remember, E stands for about 2.71. So you can type in your calculator 12 times 2.71 squared. Or you can actually use an E button if your calculator has one, and most scientific calculators do have an E. You find him on typically the regular screen on the front. Usually he's above another button, so you may have to use your second button first. But you would get approximately 88.7 for this first one. So this is the simplified answer. This is the decimal approximation for what it actually equals. Okay, let's do b here as well. 6e to the 3rd. So 6 times e raised up to the 3rd power in my calculator gives me 120.5. So approximately 120.5 is the decimal approximation. This is the simplified answer. So we can work with e just like we work with it about anything else. Let's do one more like this. Notice there's an x up there. Don't let that fool you. Don't let that make you get nervous, okay? We have 4e to the 2x all taken to the 3rd power. So remember when we have an exponent out here, we're basically going to give the exponent to the product or the things on the inside. So we have a 4 to the third power. And then we're going to have an e to this power onto that power. That's when we multiply the exponents. So what is 3 times 2x? 6x. So I can calculate the 4 to the third. That would be just 64. But e to the 6x power, I don't know what x is, so I can't calculate a decimal approximation for this one. All I can do is figure out his simplified form. So we work with e just like we work with anything else. So what else can we do with e? Well, we can graph e functions as well. Functions that contain an e. Remember, it's just like 2.71. So let's take a look at this. Let's graph this one in your notes, okay? This is graphs of what we call the natural base of e. And it's an exponential function because it's got an x up there in the exponent, okay? No log on this, just an exponential function. And notice my table of values. The x values, -2, -1, 0, 1, 2, no big deal. And we're going to plug those in. So we're going to calculate, this would be y equals e to the -2. And this next one I would type in e to the -1. And I would type in e to the 0. Constantly expecting to get decimal answers here, guys, because 2.71 raised up to a power is not necessarily going to work out to be pretty, okay? So e raised up to the -2 power is 0.135. E raised up to the -1 power is 0.37. E raised up to the 0 power is 1. E raised to the first power is 2.71. E squared is 7.4 approximately. So if we were going to graph this, -2, there we go, 0, 1, 1, 2.7, 2, 7.4. Look at this. This looks familiar. This is an exponential growth, okay? Exponential growth. He is a growth graph. He just doesn't have the same look, okay? E is like a base of 2.71. So yeah, it makes sense that if we take something like 2.71 repeatedly to powers, we would be making it grow. Okay, so remember our rules for domain, range, asymptote? I'm going to add those on here. The asymptote again, right here. I would say the asymptote is where y equals 0. Notice it cuts through the y-axis at 0. The range is in relation to that asymptote. The domain, my x values, what are they doing? So this time my domain is all reals. Okay, check them out. My range is going to be a description of what those y values are doing based upon that asymptote, okay? So think about that 0. My y values are greater than 0. Awesome. So there's a growth graph that actually had the letter E in it. What about this one? This will be our last graph that needs to go in your notes. So the graphs of another E graph here. Well, look at this one. It's e to the -x plus 1. So when we go to make a graph, we're going to type in e. Now if I'm going to plug in -2, it'll be negative a -2 plus 1. Well, if you negative a -2, that's like +2, right? So it's like e squared plus 1. That's 8.4. Okay? And the next one would be like e to the -1 plus 1. Notice there's a negative in the equation. So it's like e to the first plus 1. So that'd be about 3.7. E to the 0 plus 1. E to the 0 is 1 plus 1 more makes 2. E to the -1 plus 1. Remember the negative sign was in the equation. So e to the -1 plus 1 is 1.4-ish. And then e to the -2 plus 1. Let me see if I can get that one here. Yep, 1.14. So if we take a look at this, -2 up 8.4, -1, 3.7, 0, 2, 1, 1.4, 2, A little bit more than that. Look at this. This one is a decay graph. And this time, the asymptote is in a different spot, okay? This is a decay graph. What part of this function makes him a decay graph? Right there. That negative sign makes him a decay. Okay, that's what makes that guy go from growing to decaying. Where's my asymptote? Right here is the leveling off there. Okay, so my domain would be all reals, my range, y, and my asymptote, y is equal to 1. And so my range would be y is greater than 1. So think about this whole thing with as e is just a number. It's just a way to write a number. We can still graph with them. We can simplify with them. It's not that scary, okay? So thank you for taking good notes, and we'll continue to work with e.